This is a recording of the 2.2a worksheet. Remembering that on this particular situation, we're taking a lot of limits as x approaches infinity, or x approaches negative infinity, or x approaches a value of x from the left or from the right. There weren't problems like these two in the example, so it's really important that you get these two from the worksheet video. And what we have to understand is that when we take the limit as x approaches infinity of a sine or cosine function, remember that a sine or cosine function just, it goes, the amplitude, it goes back and forth from 1 to negative 1, 1 to negative 1, 1 to negative 1, 1 to negative 1. So what you want to think about this is that the numerator is some number between negative 1 and positive 1. So it's a small number over a really big number. So if it's a small number or over a really big number, this limit is simply going to go to 0. And it doesn't matter whether we go to positive infinity or negative infinity. It is a number between negative 1 and 1, that's how you want to think about it, over a really big number. That goes to 0. So the horizontal asymptote here is y equals 0, both to the right and to the left. Sometimes students will get this confused with that sandwich theorem problems that we did and try to multiply this by 2 over 2. But that's when we're taking the limit as x approaches 0. Don't get that confused with when we're taking the limit as x approaches positive or negative infinity. Problem number 4. The limit as x approaches infinity of this rational situation. Notice that the degree in the numerator is larger than the degree in the denominator. The degree in the numerator is a cubic. The degree in the denominator is a linear. So the degree is 3, the degree is 1. If we want to find the end behavior asymptote, which we're going to do here, we'll have to do long division. But to just find the limit, all we have to do is look at the dominant term over the dominant term. And we're going to write that down. I'm going to write it down right here so you can see it. It's simply 3x cubed over x, and that reduces to be 3x squared. When you consider the ratio of the dominant terms, if I plug infinity in and square it, it's going to go to positive infinity. That's my limiting value. Anytime the numerator grows faster than the denominator, the answer is always going to be infinity or negative infinity. We just have to determine which one. The limit as x approaches negative infinity here in this particular problem is still going to go to positive infinity because a large negative number squared still turns positive. So it's still going to go to positive infinity. Really, you can summarize these rational situations in this fashion. If the degree in the numerator is larger than the degree in the denominator, the limit as x approaches plus or minus infinity is always going to be either positive infinity or negative infinity. If the difference in the degree of the numerator and the denominator is an odd number, one will go to positive infinity, one will go to negative infinity. However, if the difference in the degree of the numerator and the degree of the denominator is an even number like we have here, it's an x squared, they're both going to be the same. They're either going to go to positive infinity or they're both going to go to negative infinity. You just have to determine which one. To determine any horizontal asymptote, there is no horizontal asymptote, but there is a quadratic asymptote here that we can do long division on to be able to determine. Now I may come down into here a little bit, but if I did 3x cubed plus 0x squared minus x plus 1, okay? And I divided that by x plus 3. And this probably would have been a good time for me to show you synthetic division because it doesn't take as much space, okay? But what am I going to multiply x by in order to get a 3x cubed? I'm going to multiply by a 3x squared. 3x squared times x is 3x cubed plus 9x squared. And remember, I never say subtract. I always say change the signs and add. So I'm going to make that a negative, and then I can add them up. These cancel. negative 9x squared minus x plus 1. What do I have to multiply x by in order to get a negative 9x squared? A negative 9. That's going to give me negative 9x squared. Negative 9x. Negative 9x squared minus 27x. Again, I'm going to say change the signs and add. 27 minus 1 is 26x plus 1. What do I multiply x by in order to get a 26x? A 26. Okay? So that's 26x plus, it turns out to be 78. It really doesn't matter. If you change the signs and add, your remainder is negative 77, but we don't care about the remainder over the divisor. That goes to 0. This will be what models the n model behavior. 3x squared minus 9x plus 26. And really, think about this. As x goes to negative infinity and positive infinity, that this really just becomes insignificant, right? This dominant term is going to dominate the behavior. But this would be the complete end behavior model if we wanted to have the complete end behavior model. Okay? I'm not going to have you find this if they're parabolic or cubic, but there's an example of how we can get a parabolic end model behavior. Okay? To me, problem number 6 is a much better question. Here's what I like about 26. These definitely are on the AP test. Okay? These absolute value situations. And this is why in class we've discussed the fact that we really want to be able to rewrite absolute values in piecewise format. So I'm going to write it right in here, this little spot right here, and I'm going to say, really, this function is in 2 pieces. If x is less than 0, I have to say 2x minus 1 over negative x minus 3. Notice I'm only negating what's inside the absolute value bars when x is less than 0. Okay, and I would write the second piece down here, but I'm running out of room, so I'll write it over here. Okay, and if x is greater than or equal to 0, I can just eliminate the absolute value bars. And I get this. When x is greater than or equal to 0, we can plug 0 in. Now, it is interesting in this problem, by the way, that x cannot be 3, right? Here. And over here, x cannot be negative 3, because those two values make the denominator equal 0. But those would be vertical asymptotes. If it wanted the vertical asymptotes of this function, it would be x equals negative 3 and x equals 3. Those values make the denominator equal 0. But when I'm talking about end model behavior, I'm looking at horizontal asymptotes or some other type of functional behavior on the extreme, the limit as x approaches infinity or negative infinity. Well, look what happens here now. If we look at this, the degree on top is the same as the degree on the bottom. So as x approaches negative infinity, because this defines this function to the left, I look at the ratio of the coefficients of the highest degree terms. 2 divided by negative 1 is negative 2. Here, if I go 2 divided by 1, I get positive 2. I have 2 horizontal asymptotes. Whenever the limiting value is a constant value, when we take these limits, that's the definition of a horizontal asymptote. So I have y equals negative 2 and y equals positive 2. Remembering that x equals negative 3 and x equals positive 3 would produce a vertical asymptote. So let's take a look at this on the calculator, just for fun. Are we really going to get a situation where we have 2 different horizontal asymptotes and 2 different vertical asymptotes? Okay? So we're going to look at this in the calculator right here. It's a good one to take a look at. All of these are. You have the calculator, use them use it to your advantage, particularly when you're doing the homework assignments. So the numerator is 2x subtract 1. Cursor down. I'm going to go math over the number 1, ABS. That's how you get the absolute value sign. I'm going to go x. I have to cursor to the right to get out of the absolute value sign, and then I'm going to subtract 3. Okay? I'm going to hit enter. I'm going to, just for now, I'll go zoom 6 to get the 10 by 10. Well, look at that. That's a pretty neat function. It definitely has a vertical asymptote at -3, a vertical asymptote at x equals +3, and it looks like this horizontal asymptote, it's certainly leveling off. It doesn't look like at 0. And the horizontal asymptote actually is -2 going this way, +2 going this way. Check these in your calculator. The calculator is a huge advantage on these. Okay, let's take a look at another one like this. There is going to be ones like this that pop up on tests or quizzes because we've worked on breaking down these absolute value functions into their piecewise component. Okay? Let's take a look at this one. Here's a second one. What's interesting about this particular problem, problem number 8, and again, I wish I had spaced it out a little bit more on the worksheet, but here it is. First thing that we need to recognize, hopefully, is there is no vertical asymptote in this problem. The absolute value of any number is always going to be 0 or a positive, and if I take the absolute value of something and add a value to it, that can never equal 0. That there is no vertical asymptote. We'll take a look at this one in the graphing calculator as well when we're done looking at it. The other thing is that this has 2 absolute values. So I have to look at it this way. If I break this down into its piecewise component, I have room over here. Okay? Again, the breaking point in each absolute value in this case is 0. So I simply have to look at when x is less than 0 and when x is greater than or equal to 0. When x is less than 0, like -1, this is going to make it, there's going to be a difference here. I have to negate what's in here. I have to negate what's in here. But if I write that down quickly right here, I get -x over -x plus 1. Look at the coefficients of the highest degree terms. Negative over negative is a +1. So I'll write it here. Here's my function. I had to negate what was inside the absolute value bars to make that negative become positive. However, when I look at this one, the absolute value bars are meaningless. I can just get rid of them. And so if I eliminate the absolute value bars, I just get x over x plus 1. This is why it's so important to be able to break these down into piecewise components. Because now the horizontal asymptote is 1 over, it's also 1. So it looks like we only have one horizontal asymptote here. Y equals 1. Okay? That's the end behavior model. But I want you to be able to write it like this so it makes sense. Let's take a look at this in the calculator. It's another good one to look at. Is it true that we have no vertical asymptote? Is it true that our only horizontal asymptote is y equals 1? I'm going to clear this out. Alpha, y equals, enter, math, over the number, ABS. The numerator is x, cursor down. Math, over the number, ABS, x, cursor to the right, plus 1. Cursor to the right, so I'm done with that, all of it, hit enter. On this one, I'm actually going to do a zoom 4. Zoom decimal works really well on this. That's a pretty cool function there, right? We do get a value for 0. If you plug 0 in, you get 0 out, but you get this bird-like function here, okay? But it never gets above 1. All of the values here are between 0 and 1 because I have this horizontal asymptote. So the range here is kind of interesting as well. Y is greater than or equal to 0 and less than 1 for the range. Okay, domains, all real numbers, because the denominator never equals 0. I know, it's a neat problem. All right, let's move on to the next. They end up giving you quite a few of these. This certainly can pop up on AP test. It says find the following limits by comparing the growth rates of the numerator and the denominator. That's exactly what we're doing, right? Any number that we plug in for cosine is going to produce a number between -1 and +1. 1 minus a number between -1 and +1 is some relatively small number. The numerator is always going to be small, but yet the bottom is going to grow extremely fast because we're squaring it. If the bottom grows faster than the top, the limiting value is 0. Same here. If the denominator grows faster than the numerator, the limiting value is 0. Looking at these two is essentially the same thing. Even though we're squaring this number here, when I take the sign of it, it produces some number between -1 and +1. Over a really, really big number goes to 0. Same here. It doesn't matter if it's negative infinity. It's some number between -1 and +1 over a large negative number. That goes to 0 as well. Comparing the growth rate of the numerator to the denominator is a very big concept that we have to be able to do. Okay, on these problems here, this is why we worked on graphing rational functions in Chapter 1. And we're going to continue to work on them, because this is going to say use graphs and or tables to find the limits. Well, you can do that, but we can also just sketch a graph as we go here. So we're going to do a little bit of a combination of both on these. Notice, now I'm taking the limit as x approaches a number from the right, or the limit as x approaches a number from the left. That's how we read this. What I need to recognize about this particular function is that it has a vertical asymptote at x equals 2. And this has a horizontal asymptote at y equals 1. The degree in the numerator is the same as the degree in the denominator, so 1 over 1 is 1. So let's look at some values. That's how they wanted us to do this, so we will do that. I cannot plug 2 in because it's undefined, so let's plug 3 in. If I plug 3 in here, I get 3 over 1 is 3. Let's plug 4 in. If I plug 4 in, I get 4 over 2 is 2. Plug 5 in. If I plug 5 in, I get 5 over 3 is 5/3 or 1 2/3. I could keep going. I could plug 6 in. I'd get 6 over 4, which would be 1 1/2, right? So let's just plot a few of these. To the right, 1, 2, 3, up 3. To the right, 4, up 2. To the right, 5. It looks like it's going to get closer and closer and closer to this horizontal asymptote of y equals 1. But what is happening between 2 and 3? What happens if I plug in a number like 2.5? So I'm approaching 2 from the right. Okay? So 2.5 on top would be 5 halves. And 5 halves, if I do this, 2.5 minus 2, I would get 5 halves over 1/2. And if I multiply by the reciprocal, the 2's cancel, and I get 5 back out. It's getting larger and larger and larger. The closer that I get to 2 from the right, the larger this is going to grow. Now, instead of just investigating, throwing in more difficult numbers here, how about we just know that if it goes through this point, it's got to approach this asymptote. This is a pole. I know it's going to come down here because this factor is raised to the first power. It's not x minus 2 squared. So I can come down here and take off. Now, if we want to plug in some points, we can. We can plug in 1. If I plug in 1, I get out -1. If I plug in 0, I get out 0. If I plug in -1, we get a -1 over a -3, we get a +1/3. So to the right 1, down 1, 0, 0. There's -1/3. It's going to get closer and closer and closer to the horizontal line of y equals 1. But it takes off like that. So the limit as x approaches 2 from the right goes to positive infinity. The limit as x approaches 2 from the left goes to negative infinity. We can certainly investigate through this, but I think it's so much more powerful if you know how rational functions look graphically. And you know the difference between a pole and what we're going to see as volcanoes sometimes. Okay? Let's take a look at the next problem. Similar situation on this particular problem. We have a vertical asymptote at x equals negative 3. We have a horizontal asymptote, again, at y equals 1. The degree on top is 1. The degree in the denominator is 1. So look at the coefficients of those highest degree terms. 1 over 1 is 1. So in doing it this way, we're getting better with our graphing skills as well. Okay? Now we just got to see, as we approach negative 3 from the right, is it going to go to positive infinity or is it going to go to negative infinity? And I say it's easier to do these problems graphically than it is through numbers. Pick a number in to the right of this vertical asymptote, like negative 2. If I plug in negative 2, I get negative 2 on top and 1 on the bottom. Negative 2 divided by 1 is negative 2. So if I go back 2, I'm going down 2. So I'll plug that in. Negative 2, negative 2. I can plug in some other numbers. I can plug in negative 1. If I plug, it's not a great number back out, so let's do this. Let's go 0. If I plug in 0, I get 0, 0 back out. What if I plug in positive 1? I get 1/4. Okay? Here it is. Okay? But if I plugged in, let's say positive 2, I get 2/5. Here it is. Coming like this. It's going to get and approach this asymptote. If you know the difference between a pole and volcano, again, x plus 3 is raised to the first power. If this was x plus 3 quantity squared, I would jump across. Okay? So I climb the pole before I start again. There's a quick sketch. I can see the limit as x approaches negative 3 from the right is going to go to negative infinity. And if I approach negative 3 from the left, that's what that little negative sign means. It's going to go to positive infinity. Remember, if I was going to check this, some of you are not going to want to graph it. You're going to want to just think about it. So let's just talk about thinking about this. If I plug in a number that's really close to negative 3, but to the right of it, that would be negative 2.99. Okay? And you might say, do I want to plug that in? That's not bad. The top is negative 2.99. That's easy enough. Negative 2.99 plus 3 is a positive 0.01. Move the top and the bottom decimal place 2 units, and you get negative 299. You get a large negative number. But what if I pick a number that is to the left of negative 3, but really close to it? So here I got out negative 299 when I plug it in. Now you got to think in terms of decimals, but watch. Negative 3.01, I'll actually write it down. Negative 3.01. Negative 3.01 plus 3 is a negative 0.01. Negative over negative is positive. Move it 2 decimal places to eliminate the decimal in the denominator, and you get 301 over 1, 301. When I plug a number really close to negative 3, but to the left of it, it goes to a large positive number. A lot of you can just think about it that way numerically. Others are going to want to think about it graphically when you take these limiting values around these vertical asymptotes. Whatever works best for you. 18 and 20 are some unique situations, and it's worth talking about it just a little bit to see what's happening on these, because you do get some pretty interesting graphs. Notice it says use graphs and or tables to find the limit. I would probably not use graphs here, because when you graph this is quite an interesting problem, because you get a bunch of jump discontinuities over here. But let's just talk about numbers as we approach 0 from the left or from the right. We're starting with approaching 0 from the right. I think this one's going to be easier to do by investigating numbers. A number that's really close to 0 but to the right of 0. 0.1, that's close to 0 but to the right of it. The integer value of 0.1, remember, is the closest integer that's less than or equal to 0.1. That's 0. 0 divided by 0.1 is 0. If I pick a number like 0.01, the integer value of 0.01 is 0. And 0 divided by 0.01 is 0. So as I get closer and closer and closer, this value is just going to stay at 0. As a matter of fact, all of these numbers here, okay, the graph is going to ride right along the x-axis there. And I get 0 out. Remember, it's not defined at 0 though, because we cannot divide by 0. But the limit as x gets closer and closer to 0 from the right will go to 0. So it's probably going to be similar over here, right? Well, let's see. Now I'm going to get really close to 0, but to the left of 0. Negative 0.1. The integer value of negative 0.1. The closest integer less than or equal to negative 0.1 is negative 1. Over my value of negative 0.1. Well, that's interesting. Negative over negative is going to be positive. And if I move the decimal place, 1 decimal place, I'm going to get 10 over 1. I get 10 back out. Huh. That's way up here. What happens if I plug in negative 0.01? Closer to 0, but to the left. The integer value of negative 0.01, the closest integer that's less than or equal to negative 0.01, is negative 1 over negative 0.01. Negative over negative is positive. Move the decimal point 2 decimal places. 1, 2, 1, 2. That's 100 over 1. We get 100 back out. It's just getting larger and larger. So it's an asymptote on the left-hand side of this, but it's not an asymptote on the right-hand side. That's what makes this function interesting. We actually get this infinite discontinuity to the left, but to the right we actually approach the value of 0. And if you look at this particular function in your graphing calculator, I've graphed it on the hard copy of the solutions of this, so you can kind of look at a more detailed graph, but it's going to have all these breaks in the action over here. Here is more of a nice smooth curve, okay? But it's kind of an interesting problem, all right? The good news about a function like this is I don't remember seeing the integer function even pop up on the AP test. But it's a great pre-calculus, has a lot of good practical applications. I've talked about that already. And it gives us a unique situation to look at here. So that's one reason why this is good. It's not going to get any worse than something like this in terms of trying to think about it. But if you just think about the values as they approach from the left and from the right, we can reason what this limiting value is. And that's just as important as any skill, is being able to use your mathematical background to reason a good answer. Okay? Let's talk about this. On this one, I certainly think it's easier just to sketch the secant curve. Remembering, I'll call this one, actually, I might as well go all the way up here. I'll call this 1. No, I'm changing my mind. I'm going to call this 1. I'm going to call this negative 1. Okay? This is 2. Here's negative 2. Remembering that the secant is a reciprocal of the cosine curve. And the cosine curve, the cosine at 0 is 1. The cosine at pi over 2 is 0. The cosine at pi is negative 1. Cosine at 3 pi over 2 is 0. And the cosine back at 2 pi is positive 1. And I can go this direction as well then. Got to cross before I go low. I got to cross before I go high. Everybody should be able to graph this cosine curve. And if I dot this curve in, I'm going to get something that looks like this. Notice I'm dotting it in because I'm not looking at the cosine curve. Okay? The limit as x approaches pi over 2 from the right and from the left for the cosine curve, that would both be 0. It's the secant curve. Anywhere where the cosine would cross the center line, we dot in a vertical asymptote because the reciprocal of 0 is undefined. Reciprocal of 0 is undefined. Okay? But the key part to this is then graphing the actual curve of the secant function. Remember, the reciprocal of 1 is 1, but the reciprocal of a really small positive number is a really large positive number. The reciprocal of a really small positive number here is a really large positive number. The reciprocal of a really small negative number is a large negative number, okay? Which is actually a small number, okay? But here it is. If we sketch this, now, the limit as we approach pi over 2 from the right goes to positive infinity, where the limit as x approaches pi over 2 from the left goes to negative infinity. Okay? Again, kind of a tough one because you don't know, should I be doing chart or should I graph it? That's why I gave you the option on a lot of these. Not something that I'm likely to ask, but more likely to be on an AP test. They would expect that you know what a graph of a secant function looks like and that you could potentially answer this question from the right or from the left. Certainly more likely that something like this than something like this. The next phase of this worksheet says find the following limits by applying the properties of limits. So essentially, really what I'm going to write some work down here, but how much work you show on these when you do these on the test. There is 1 or 2 of these, not a lot. Really doesn't matter. But I think it's important for you to know that if I'm taking the limit of a product, I can take their separate limits and multiply them together. So I'm going to write it this way so you see what I'm actually applying. Can I take this limit? Yeah. As x grows without bound, the bottom grows faster than the top, so the numerator, the denominator outgrows the numerator. So this goes to 0. 0 plus 1 is 1. We're looking at this rational situation. The degree in the numerator is the same as the degree in the denominator. So I look at the coefficients of those highest degree terms. 5 over 1 is 5. And 1 times 5 is 5. That easy. And a lot of you could do it without writing anything down. Okay? Now, is that going to change when we're going to negative infinity? No, it's not going to change. That's still going to go to 0. This is still going to go to positive 5. So this is going to be 5 over here as well. Okay? Are there some that will make a difference? I don't know. Let's see. Students sometimes want to do these as if it's the sandwich theorem or squeeze theorem. This is not a sandwich or squeeze theorem application. We're taking the limit as x approaches plus or minus infinity. So let's break this up though. I can take the limit as x approaches infinity by separating the numerator over the common denominator. Okay, I can take that limit and then add this limit of the sine of x over x. Okay? I'm just looking at as 2 separate limits. This cancels. The limit as x approaches infinity of a horizontal line equals that value. That's 2. The limit as x approaches plus or minus infinity of a constant is just the constant. The limit as x approaches infinity of this one. This is where we got to think about it. The top is going to produce some number between -1 and 1. The bottom is going to grow without bound. It's going to get very large. So the numerator is some number between -1 and 1. The denominator is a very large number. That's going to go to 0. If the denominator outgrows the numerator, the limiting value will go to 0. And 2 plus 0 is 2. Okay? Some students, when they see this, they want to say that this limiting value is 1. That is the limit as x approaches 0. And remember, we verify that using the sandwich theorem to verify that this limit as x approaches 0 goes to 1. But that's different than the limit as x approaches infinity. I just have to realize this is a number between -1 and 1 over a very large number. Let's do the next one. It's the same thing. It's the same setup. Whether we go to positive infinity or negative infinity, this is going to go to 2. That's going to go to 0. That is the horizontal asymptote. Both 22 and 24 have horizontal asymptotes. 26. Similar problem. Okay? I'm going to separate the numerator over the common denominator. So x sine of x over 2x squared. And then I'm going to add the limit as x approaches infinity of 2 sine of x over 2x squared. So I'm separating the numerator over that common denominator. If I added these two fractions together, I would get that. I'm just separating it now. So I can cancel. I can cancel the 2 here if I want. But it really isn't going to make a difference. The whole key to this, I can evaluate the sign at any angle, and it's going to produce a number between -1 and 1. The bottom is going to grow without bound because it's 2 times x. So I'm going to have a number between -1 and 1 over infinity. That goes to 0. And it doesn't matter if we're going to positive infinity or negative infinity here. It's the same thing because this also goes to 0. The sine of any angle between is going to produce a number between -1 and 1 over a really large number. It's going to go to 0. Good? Okay, the directions on this problem say find the vertical asymptote of the graph, provide a graph, and use the graph to describe the behavior of f of x to the left and to the right of each asymptote. Find the end behavior model as well as any x or y intercepts. Okay? So let's start. I always like to look to see if we can factor this. If we can factor the top to be x plus 1 times x minus 1, and we can factor the bottom to be 2 times x plus 2. Factor out the greatest common factor on the bottom. Why is that important? When the numerator equals 0 is going to tell us the x-intercepts. So we have an x-intercept at x equals 1 from this factor and x equals -1. Write them as coordinate points when we write the x-intercepts. We'll write them right here. 1, 0, -1, 0. So I can plot those 2 points. That's a good start. Do we have a vertical asymptote? Well, we have a vertical asymptote, any number that makes the denominator equal 0. X equals -2. So I'm going to write that right here. And I might as well dot that in. X equals -2 is right here. Okay. Do we have a horizontal asymptote? What is the end behavior model? Let's go ahead and find the y-intercept quickly here. If I plug 0 in for x, I get -1 over positive 4. 0, comma, -1/4. So it does do that. It's below that just a little bit. Okay. Well, what else is going on here? The degree in the numerator is larger than the degree in the denominator. So we have to do long division to find the end model behavior. X squared, don't forget we have to go 0x minus 1. And I'm going to divide this by 2x plus 4. When do we ever use long division? I have a lot of algebra teachers ask me that. Here it is. What do we multiply 2x by in order to get an x squared? A 1/2 x. 1/2 x times 2, we get x squared. 1/2 x times 4, positive 2x. Instead of subtracting, we will change the signs and add. -2x minus 1. What do we multiply 2x by to get a negative 2x? A negative 1. Negative 1 times 2x is a negative 2x. Negative 1 times 4 is a negative 4. Change the signs and add. Negative 1 plus 4 is 3. I'm going to add 3 over that common denominator. But remember, if x goes to infinity, this is going to go to 0 because the denominator is going to grow faster than the numerator. So we can cancel that out. That's the end behavior model. Y equals 1/2 x minus 1. That's going to make a big difference when we go to graph this. So my slant asymptote, because the degree on top was 1 larger than the degree on the bottom, has a y-intercept of negative 1 and a slope of up 1 over 2, down 1, back 2 when I dot that in. There's my slant asymptote. I'll do it in this green marker so you can see it a little bit better. Okay. Now, we could plot some more points here, and I give this to you so that you can do that. But the fact that we're graphing these 3 points here is going to tell me how this graph is going to look. Here's what I know. It's got to go through these 3 points. It's got to cross through here, cross through there. It's got to hit that y-intercept. Okay? And it's got to approach this slant asymptote. The denominator, if you know the difference between a pole and a volcano, the denominator comes from a factor raised to the first power. And I know we haven't seen many volcanoes, but we will. I have to slide down before I start again. I could have plotted a few points here and maybe it'd be worth the while to do that, but that's good enough. Got a good picture of it. So the limit as x approaches, remember our vertical asymptote was negative 2, so I left that blank there so you'd have to fill it in. I didn't want to tell you what it was. The limit as x approaches negative 2 from the right. Start to the right of negative 2 as I get closer and closer and closer to negative 2. This is going to positive infinity. But the limit as I approach negative 2 from the left, as I'm getting closer and closer and closer to negative 2 from the left, this is going to negative infinity. Go. On problem number 30, it's very similar. Can we factor the denominator? Well, are there 2 numbers that multiply to be negative 6 and add up to be negative 5? Yes. Negative 6 times 1 multiplies to be negative 6, adds up to be negative 5. I'm going to make the outside multiply to be the smaller number. Well, that's easy. It's positive 1. So it's got to be an x here and a plus 1 here. First times first to get the first. Last times last to get the last. Remember, when we're factoring this, we're just doing O-fly instead of FOIL. Outside first, last inner. O-fly. Do we have vertical asymptotes? We have 2. We have vertical asymptote at x equals 3. We have a vertical asymptote at x equals negative 1/2. That's why you have more blanks here. So I'll put my x equals 3 here from the right, from the left. This is going to be my negative 1/2 here. You got to write small. Okay. What about the end behavior model? Sorry, I'll put that down there. So I put the 3 here and here. I put the negative 1/2 here and here. Okay. What about the end behavior model? Well, the degree in the numerator is a linear function. The denominator is quadratic. So the degree in the numerator is less than the degree in the denominator. That means y equals 0 is the end behavior model, the horizontal asymptote. Do we have an x-intercept? Is there a value of x that makes the numerator equal 0? Indeed, there is. When x is 1, the numerator equals 0. 1, 0. What about a y-intercept? If I plug 0 in for x into that original equation, if I plug 0 into the numerator, I get out 1. If I plug 0 into the denominator, I get out negative 1/3. So negative 3. So it's negative 1/3 is my y-intercept. So let's graph those 2 points. Graph the whatever asymptotes that we have here, right? As a matter of fact, there's a lot of material that we can graph now looking at these values. Let's start with the 2 vertical asymptotes. X equals 3. Goes right through here. X equals negative 1/2. Might not be the prettiest, but it looks like this. Okay, somewhere in between there. What about horizontal asymptote? We said we have a horizontal asymptote right on this. Okay. What about any intercepts? Well, this is what's interesting. We have an x-intercept right here. And that is the only x-intercept. And we have a y-intercept right here, negative 1/3. Well, that means in here, if I just start here, I know it's got to go like this. Okay? I can't cross through again. So I can plug some values in. I could plug 2 in to see where it's going. Okay? But I know it's not going this way. It's got to be coming up here. It's going to look like this. It's going to approach that. Okay? I also know that both of these vertical asymptotes come from a binomial factor raised to the first power. So this is going to slide down the pole before it starts again. This is going to climb the pole before it starts again. There are no other x-intercepts for it to go through. So the fact that there are no x-intercepts is just as important as finding this one, because we know it's not going to cross through that horizontal asymptote, and we're not going to have a bump outside of here. It's going to look like that. So let's take a look at these. Once we get a picture of it, I think that's the easiest way to deal with this. Now let's come back and talk about the limiting values here. As we approach 3 from the right, this is going to go to negative infinity. The limit as x approaches 3 from the left. Remember, that means from the left. I have to be to the left of 3. Oh, it's going to positive infinity. The limit as x approaches negative 1/2 from the right. So I'm to the right of negative 1/2. I'm getting closer and closer and closer to x being negative 1/2. The y value is getting larger in this direction. And the limit as x approaches negative 1/2 from the left goes to positive infinity. If you can get good sketches, many times that is the best way to determine what your limiting value is going to be. Now we come back to some pretty easy problems on problem number 40. To find a power function and behavior model for a polynomial function, it just is y equals the dominant term. That's it. This simply means that as x grows large in the positive or negative direction, these other terms become insignificant compared to this one. This will dominate the graph, and this graph essentially will look like this graph on the extremes as x goes to positive or negative infinity. 42. Find a power function and behavior model and identify any vertical asymptotes. So on this particular problem, we're not looking for x-intercepts, so there's no need to factor the numerator. But we do need to factor the denominator. X plus 2 times x minus 2. The numerator we can leave. It's not factorable, by the way. Our end behavior model. Look here. The degree on top in the numerator is the same as the degree in the denominator. So I look at the coefficients of the highest degree terms. Y equals 3. That's the end behavior model. We do have 2 vertical asymptotes. X equals 2 and x equals negative 2. They're both poles, by the way. Don't look at this. It's after it's factored. It's x plus 2 to the first power, and it's the binomial factor of x minus 2 to the first power. Let's take a look at this. Okay? Now the degree on top is larger than the degree on the bottom. we shouldn't have to factor this again. We can tell x equals 2 and x equals negative 2 is going to be the two vertical asymptotes. Okay? And if it wants to know a power function and behavior model, technically you should do long division here to find out the complete end behavior model. But on this particular one, I'm simply going to say this. If I look at the highest degree term in the numerator over the highest degree term in the denominator, negative x to the fourth over x squared, negative x squared. It's going to look like y equals negative x squared. Now granted, if I did long division, there might be some other terms that would come out in this end behavior model. But as x goes to positive negative infinity, those terms are going to be insignificant, just like they were in problem number 40. Okay, these problems here I really like. We have to think about the end behavior model here. And what we need to know is exponential always outgrows polynomial. So as x gets really large to the right, e raised to an exponent, this is going to grow much larger than a linear situation. So this is going to go to positive infinity. This models it. But the interesting part on this one, as x goes to negative infinity, think about this. If I plug in negative 10, e to the negative 10th, okay, is 1 over e to the 10th. That's going to go to 0 as x gets large in the negative direction. So the left end behavior model is going to be the linear function. Let's take a look at another one of these. So now the right end behavior model, if I plug in 10, that's to the right, it's going to the right, or 100. This is 1 over e to 100th power. That's 1 over a really large number. This is going to go to 0 as I go to the right. So the right end behavior model is going to be this parabola. But as I go to the left, this function here, when I square, that's a large positive, but not nearly as large as this. Exponentials always outgrow polynomials. So if I plug in negative 100, e to the 100th power, this is going to grow much more rapidly than even 100 squared. So the left end behavior model is e to the negative x. This will outgrow this in the negative direction. Let's take a look at another one. These are all really good. Okay? Right end behavior model. If I plug in a large positive number, 100, I get 100 plus the natural log of 100. 1,000 plus the natural log of 1,000. Remember, a natural log function does this. It actually starts to level off, or a linear is going to do that. So a linear function outgrows the logarithmic function. So the right end behavior model is going to be y equals x. Okay? But the left end behavior model, if I plug in negative 100, notice there's absolute value bars here, okay, to make it positive. But this number is still going to outgrow that number. So y equals x is also the left end behavior model as well. You're just determining which function is going to outgrow the other. Look at this. This is an interesting problem as well. If I plug in a large positive number and square it, that's going to be a large positive. This is some number between negative 1 and 1. This really has little impact at all as x gets larger and larger and larger. Actually, it has little impact as x gets larger and larger and larger in the negative direction, because when I square it, it turns positive, and this is some number between negative 1 and 1. So the only impact that this sign of x will have on this function is for values around the origin. Outside of that, when I look far to the right of this graph and far to the left of this graph, it's just going to look like the parabola y equals x squared. Which part of the function outgrows the other when I look at a large positive value or a large negative value? That's what you're determining when you're determining the end behavior model of these examples. Okay, true, false, multiple choice. We'll end this up. It's a long video. I know you'll have some time to work on it though. It is possible for a function to have more than one horizontal asymptote. Justify your answer. True. We've looked at a couple of them. Here's a good example. The absolute value of x over the absolute value of x plus 1. That has two horizontal asymptotes. Oh, let me say that again. This one actually only has one horizontal asymptote. But you can have more than one horizontal asymptote if we do this. If we have the absolute value of x over x plus 1, no absolute value on the bottom, right? This will have positive 1 as an asymptote and negative 1 as a horizontal asymptote. So the absolute value of x over x plus 1 is a good example. Okay, there's a good example. All right, so that's my justification. 60, true or false. If f of x has a vertical asymptote at x equals c, then either the limit as x approaches c from the left of f of x equals the limit as x approaches c from the right of f of x equals infinity, or the limit as x approaches c from the left equals the limit as x approaches c from the right equals negative infinity. That's false. You just have to have one of them. It doesn't matter. They don't both have to go to negative infinity. Just one does. This is true if you have a volcano. Or this is true if you have a volcano that opens downward, right? That goes this way. But they don't have to both go to positive. Only one of them has to go to positive or negative infinity. Okay? So this would be false. And you only have to have one direction go to infinity or negative infinity. 61. Multiple choice, the limit as x approaches 2 from the left of this function is going to go to which one of these? Okay? This is a vertical asymptote, but I'm just going to plug a number really close to 2, but to the left of 2. How about 1.99 over 1.99 minus 2? That's 1.99 over negative 0.01. Move it 2 decimal places. Positive over negative is a really large negative number. This is going to go to negative infinity. Okay, on this one here, we do have to be careful because a lot of students think this is going to infinity or negative infinity. So they think this is some number between negative 1 and 1. Or that's not the case here. If we plug in 0, 2 times 0 is 0, but the cosine of 0 is 1 over 0. When we get a number divided by 0, that's undefined. That does not exist. Okay? Problem number 63. Now, this is one where you would have to use your calculator because this is really one of those sandwich theorems. And the bottom line is we can do it algebraically by multiplying this by 3 over 3. And I can say this is the limit as x approaches 0 of this factor of 3 times the limit as x approaches 0 of the sine. I want to pair this up. The 3x is up. The sine of 3x over 3x. The limit as x approaches 0 of a constant is that constant value. The limit as x approaches 0 of the sine of 3x over 3x is defined to be 1. And 3 times 1 is 3. But you could use your calculator on this. We're going to learn an easier method. That easier method is going to be called L'Hopital's rule in a future chapter. Last one. Sorry about all the interruptions in making of this. Which of the following is the end behavior model? The degree on top is the same as the degree on the bottom. Look at the coefficients of the highest degree terms. We have a horizontal asymptote at y equals 2. Therefore, the end behavior model is 2. Okay?